Okay, good evening, students. So we're looking at an important topic again this evening, and that's energy quantization. Energy quantization. We know that the energy of an electron are in a kind of discrete unit that we call quanta. So when you find a situation like that, we say such energy has been, that is, an atom can be quantized. But the whole process of that discrete unit, energy of electrons and all of that, the whole process is what we refer to as energy quantization. When you get to the university, you'll be hearing something like Bohr, you'll be hearing Obama series, Paschen series, Barker series, and even P-Font series. Okay, so now, but that is particular about calculations and particular about solving, formula solving and all that. So there are few scientists that contributed on the energy quantization. Notable among them is Bohr. We have Albert Einstein of photoelectric emission and others. We even have one which we'll be coming up with later, and that's the Bohr of wavelength. Okay, so well, let's quickly look at this now. The photon, the energy of the photons is actually given as this. Okay, but before I start with this, it's important I talk about ground state and excited state. Please listen very well. The ground state is, so according to Bohr, is the most stable state of the atom. Is the what?
Most stable state.
So atom will prefer to be in that ground state. So but at that level, the Lyman series, the lowest series, the energy, the atom wants to go up. And to move up, you have to absorb what? Energy. So to move from a lower level to a higher level, we call that absorption. We call that what? Absorption. Energy must have been absorbed. So as you move to a higher level, we call that an excited state. We call that what? An excited state. So at the higher level, you could also come down, and that's emission. That's what? Emission. If you move from lower to higher, absorption. The higher to lower is what? Emission. Please take note of that. Now, we have a general formula actually that we can write, which is 13.6 watts electron volt. Please write down. We have something like this. And this one, what does N represent here? Normally, we usually use principal quantum number as N. So it represents the energy level. So N, maybe level 1, level 2, level 3, as a case may be. So take note of that. And why the EV there is the electron volt. Is the what? The electron volt. Is the what?
Electron volt.
Is the electron volt. Is the electron volt. Now, so I just showed you something now. The energy of the photons is equals to H multiplied by F. What is H? The Planck's constant. And Planck's constant here is 6.03 times 10 raised to the power minus 34 joules second. And this is our frequency. Now, we know also there's a relationship between frequency and speed. So we have our frequency to be speed over lambda. Frequency is speed over lambda. And so putting this here, we have this over lambda. So this is another formula you must take note of, where you have your energy equals to Planck's constant multiplied by speed of light over lambda. The c there is the speed of light, which is 300 million per second, or 3.0 times 10 raised to the power 8 meter per second. Okay, so that now, what's the next thing we need to note here? we want to know Einstein photoelectric what? Emission. Einstein photoelectric emission. Now, please pay attention very well. Einstein photoelectric emission, I like to put it this way. Maybe this may not be the way you were taught in school, but please follow what I'm giving you. This is the energy of the photons, this is the kinetic energy, and this is your work function. So I take this to be my own general. So this may not be the way you will say it in textbook, but by the time I'm done, you'll see that it's exactly what you've been saying anyway. Okay, so let's go now. So we have this. We understand that our work function is HF times naught. Is HF times naught. Another formula to know. Please, you need to note all of these things. Now, this is Planck's constant, and F naught is called threshold frequency. What do I call it?
Threshold frequency.
So it's called threshold frequency. Please take note of that. So we have E equals to EK plus. Now we also have E. The EK here, kinetic energy, is equals to half mv squared. So I can put half mv squared here plus hf naught. I guess I'm not so fast. Are you following?
Yes, sir.
Okay. So E equals to this and equals to this. Now, also note that EK is equals to electron volts. Therefore, our equation can change to electron volts multiplied by H naught. Electron volts, since the kinetic. Can I wipe the board?
Yes, sir.
Can I wipe the board?
Yes, sir.
We have this. Our E is HF, we know that already. This is electron volts. This is HF naught. Now we could make any one subject of formula very easily. So we could have H this, HF naught equals to EV, so that my V, HF naught, H this over E. This is called stopping potential. Please write it down. That's stopping potential. This is Planck's constant frequency, Planck's constant threshold frequency, and this is electron. And the charge of one electron is 1.6 times 10 to the power minus 19 coulomb. So it's constant value. It will be given. Also note that 1 electron volt is equals to 1.6 times 10 to the power minus 19 joule. I repeat. Also note that 1 electron volt is equals to what?
1.6 times 10 to the power minus 19 joule.
Yes. Minus 19 joule. And in case you also wanting to join my community where I'm building up young scholars, I'm building up people who become a pace setter in their various field of endeavor, then you might have to show your interest also in the comment section, and I'd like to add you to the platform, to my community platform. Thank you very much, and God bless you. Bye.